Hello, my name is Novin, and I'm going to present my time series analysis course project. So, uh, in this presentation, I will explain my experiments for two different time series that I was supposed to analyze. First one, it is a time series WL45, which I experimented with ARIMA and SARIMA models and Holt-Winter family. At the end, I will come up with a conclusion which model was the best. The second one is TSO93S, which I experimented with SARIMA models, as well as Arimax with regressor TS1422S, another time series. And similarly, I will come up with a conclusion of which of these models performed best. So the first time series, here's a data set by the United States Geology Survey. It includes surface water monthly data. Each observation is a mean value of the surface water with total observations of 993 from January 1930 to September 2012. As we can see in this plot, this time series seems to be a stationary, or rather stationary. It's not obvious if we need to do any pre-processing, but again, looking at the ACF, there seems to be some seasonality, more or less considerable. So for that, I tested with two different stationarity. This time, I tested this time series with two stationarity tests. One Phillips Perron and the other augmented DQ Fula. And based on these tests, there is no stationarity, but again, looking at the ACF, we should be cautious. Although these tests are not revealing any non-stationarity, we should make sure, because it's not definite answer. It's not something totally reliable. If these tests reveal that there is a non-stationarity, then we could 100% be sure there is something. But if not, there is not any, based on the outcome of these tests, we cannot say for sure. So because of that, I came up with two different set of experiments. First, ARIMA, or non-seasonal ARIMA models. As we can see in this plot, there is up to at least 3 autoregressive terms existing, and here there could be a few moving average terms. So I started with the simplest model that I can think of, which was ARIMA 300. But as you can see, based on the Lungbox statistic, it is not very useful, as the residuals are correlated. And the other model that I found, which was this time useful, based on the Lungbox, as we can see, and the residuals are not that correlated, although there are slight bumps over the limits of the ACF. It was ARIMA 303, which includes 3 autoregressive and 3 moving averages. So to make sure that this series include any non-stationarity, I came up with seasonal differences. As we can see here, a seasonal difference with period 12 and seasonal and ordinary difference here. Obviously, combination of these two differences is an overkill because of these negative values in the PACF that we can see, also in ACF. So I stick with the seasonal difference. And based on this, again, rather the same number of autoregressive and moving averages exist for the non-seasonal part. But there is also like up to maximum 3, based on this PACF, maximum of 3 seasonal autoregressive here, and there might be some seasonal moving averages as well. So because of that, I came up with 2 different SARIMA models. I included 3 autoregressive terms, as I explained. In one of them, I included 1 moving average, the other one 3 moving average for the non-seasonal part, for the sake of variation. And obviously, we have this seasonal difference. And And as we can see here, like there is a bump here for the seasonal moving average. So because of that, I have this term moving average, seasonal moving average. So these two models are different in two parts, as we can see, in the moving average of the non-seasonal part and the autoregressive of the seasonal part. These are the forecasts for all these four models that I tested, and obviously the ARIMA models, non-seasonal ARIMA models, are not performing very well, but the SARIMA models are rather decent. So, but it's not really obvious which one is the best. So, looking at the error measurements of each of these models, obviously SARIMA models performing beating the ARIMA models. But again, picking which one is best is not an easy job to do on the error measurements. Based on these, we would like to pick this second SARIMA model. But it's at the same time best to look at the archaic information criteria. So because of that, I looked at that, and as we can see, on the contrary, based on AIC, the first SARIMA model is better. So because I chose SARIMA model as the best model that I found, this would be the model formulation. This is a general form of the SARIMA model. And the terms should look like this. And if we expand, we will get this model. Although I should note that I only used one autoregressive term for the non-seasonal part. Because with three terms, it would look like a very huge formula, and due to lack of time, I chose to do that. But again, I plugged in the values that feed it for the original model. So this would be the ARIMA and SARIMA family models. Experiment, and the next one is the Holt-Winters family. I tested three different models in this family, the exponential smoothing Holtz and Holt-Winters models. But obviously, looking at the residuals of each these fitted models, they're not really good models, and we cannot rely on any of them, obviously. But if you want to think about intuitions, because this time series has got only seasonality and not really any trends, the exponential smoothing is supposed to work better. But again, it seems that the Holtz from these residuals is the best one among these three. The Holt-Winters is an exponential smoothing, essentially, with justification for the trend and seasonality, having all alpha, beta, and gamma terms, parameters. So this would how the forecast looked like for this family. And as we can see, the Holt-Winters captured the general pattern of the test data, but the level is not correct, and it's totally off. Among these, Holt's method seems to have a decent prediction. But let's look at the error measurements. So based on error measurements, the first mean absolute error shows that Holt's method is performing better, but comparison of the other error measurements, exponential smoothing, is performing better. So it's a very close call to say, but if I would like to choose between Holt's and exponential smoothing, I would go with the Holt's method, because the prediction intervals at least contain the test data. And while the exponential smoothing is not really, even the prediction intervals are hardly containing the whole forecast horizon test data. So this would be the Holt's method. Mathematical formulation based on the parameters found, alpha, beta, and gamma. So as a conclusion for the first time series analysis, we can see different models, the best models from each family here. It shows the forecast of each of these methods. And so I picked SARIMA as the best model and Holt's method, the second family, but obviously SARIMA outbeats also the Holt's method. And So we basically performed different criteria for picking the best model, but most importantly, the archaic information criteria used for the Serima models to pick one. Obviously, there could have been other transformations that might have helped, but due to lack of time, again, I did not tested those. So for the second part, I had this time series traffic accidents and casualties on the road with a total of 336 observations from January 1990 to December 2017. Obviously, we have some local trends here and here, but then we need to do some stationarity tests to make sure if there is such trends or such non-stationarity in general. But more importantly, in the ACF, we can see some strong seasonality. These are the tests, and they're not suggesting any non-stationarity. But again, based on experience, we should try different differencing to make sure. So here I have got two different differencing, and we can see the seasonal difference, which seems to be okay, and actually makes the series stationary. But on the other hand, the seasonal and ordinary difference is an overkill again because of the negative values that appears in the correlation plots. So I rather stick with the seasonal difference here as well. So here, because we had like seasonal difference, I only tried the seasonal ARIMA, two different models. And as we can see in this PACF, there are up to 3 non-seasonal autoregressive terms, and there could be 1 or 2 seasonal autoregressive terms. Similarly, for the moving average, we have up to 2 or 3. We can have even more non-seasonal moving average terms, and there might be some seasonal moving average, but it is not obvious that it will help from this ACF plot. So the models that I picked based on the analysis on this plot are these 2 with 3 moving average, non-seasonal moving average terms, and more importantly, we have this seasonal differencing. But the only difference between these 2 models is this seasonal moving average term. So to make sure which one is the best, again, I use the archaic, which I will explain in a few slides. So these are the forecasts of these 2 models. It is not really obvious which one is the best. Maybe with this one is best based on the prediction intervals, but it is not obvious. So let's look at the error measurements and see what's the performance of each model. So these 2 models, Serima models, we have here the MAE for the second one is best one, also the MSE, but not on the MAPE. So again, it's not really obvious. If you jump to the archaic information criteria, we can see that the first model actually is the better one. Not the simpler model, but it is the best model. So because we use the Serima model, this is the general formula. And if we expand these terms, it will look like this. And if I plug in the values that found by the fitting process, optimization process, it will look like this. But due to lack of time, again, I did not really simplify this equation. It should have looked like ZT on one side and the other terms on the other side of the equation. For the regressor time series, I used TC1422S, which is a freight traffic on railways. This was the only data set that I could find in the second directory that I could use as a regressor for the Arimax, which had, to some extent, the same alignment of time. The rest of the time series were not really matching the dates of the first time series that I had to analyze. So the total number of observations in this time series is 326 from January 1991 to February 2018. So because of this 12 months difference in the beginning and 2 months difference in the end, I have to cut off the end part of this time series and the first part of the first time series and make it align together. Obviously, there is some global trend, although in the first part it is upwards and downwards on the second part. There is also seasonality. As we can see, it is decreasing very slightly. There is a high chance of seasonality, but then we need to make sure of that by testing the differencing. And so these are the steps that I take, aligning and cross-correlating to find which lag of the regressor is appropriate for performing the Arimidex, and finally applying the Arimidex. Again, this is the stationarity test that I do by default to make sure of some obvious non-stationarity. So we can see there is definitely a non-stationarity because the p-value is above the critical value, which is 0.01. And so the TC1422S stationarized using the seasonal difference of period 12. I tried different differencing, but again, ordinary and seasonal difference together was an overkill because of the same reason that explained on other time series and experiments. So here, if you can see, if you take a look, there is again up to 3 maximum non-seasonal moving autoregressive terms, and it could be up to 2 or 3 maybe seasonal autoregressive terms. Similarly, we have a few non-seasonal moving averages here. So the next thing to do was to find the appropriate number of lags, and this is the cross correlation of 2 time series after making it stationary, both of them. It is not really obvious what lag is appropriate, but it seems that lag 1 is good. So because of that, I went to the pre-whitening method, and basically we we feed a model on the regressor time series and find the residuals, and apply the same model on the response time series and find the residuals of that too, and then cross-correlate the residuals. And cross-correlation of these two residuals reveal that lag 1 is indeed appropriate for doing the Arimidex. So the next step was to apply the Arimidex, and this is what it looks like. So the Arimidex 301 for the non-seasonal and 110 for the non-seasonal part I chose. I tried different variations. This seems to be the best one, although it has got some discrepancies, as we can see from lag 12. Plus, it has got uncorrelated. It has got correlated residuals, and exactly as at lag 12, there is a bump over the limits of the ACF plot. So this is definitely not the best model that we can have, but due to lack of time, I did not explore it anymore. And let's see the results. So the general form of the Arimidex model is like this, and because I used the SARIMA for the residual part, the formulation would be looking like this, and the output of the algorithm of the model. So we have got these optimized parameters of the model, and if you write down the residuals part of the Arimidex, it will look like this, and in general the model will look like this with these terms. And after plugging in the optimized parameters, we will get such a model. So as a conclusion for the second time series, I tried 2 different SARIMA models and 1 Arimidex, and it turned out that the SARIMA performs best. This is the 95% prediction intervals. Of course, again, other transformations might have helped, but again, due to lack of time, I did not try that. So with this, I conclude my project. Thank you for your attention, and if there was any feedback, I would be happy to receive it in my mailbox novin@ut.ee. Thank you.